Hello everyone. Today we are going to look at this paper which is called as Kolmogorov Arnold Networks. This particular paper has been released quite recently and it has been making a lot of waves. When I read the paper, I found the writing to be very simple and easy to understand. So, from that point of view, it is a very nicely written paper and it has been almost written like a tutorial. So, it is fairly easy to follow. Uh, so my objective in in today's video would be to give a brief background of what is covered as a whole in this paper, and we are going to dive into the individual aspects of the paper a bit later in a separate video. So let's go through the abstract. Okay, so in this paper they have proposed an alternative to multi-layer perceptrons, and these networks are being termed as Kolmogorov Arnold networks. So the main difference uh, in this network when we compare it with multi-layer perceptrons is that in MLPs you have activation functions on the nodes of the network, whereas CANs, which are Kolmogorov Arnold networks, have activation functions on the edges of the network instead of the nodes. We will look at what this means in detail, but this is one of the major difference when we compare MLPs with CANs. So these are two completely different approaches, and neural networks are known as function approximators. Through their complicated architecture, they can be used to approximate any function. Uh, so conceptually speaking, cans also achieve that. Cans can be used to approximate any given function. The difference though is that we don't use weights and biases for every different node over here. Instead, every edge is represented by an activation function, which is a B-spline function. If you don't know about a B-spline function, it is completely fine. For understanding cans, it is not really required. So, what exactly are Kolmogorov Arnold networks? So, I'm just going to explain this to you using a diagram. Uh, okay, so let's get started with this. Right. So, let's take let's take a network with three layers. Let's say we have two neurons in the first layer, and we have three, four, five neurons in the second layer, and we have one neuron in the final layer. Now, in a traditional multi-layer perceptron, what you would have is that at every layer there would be connections with each of these two neurons, like this, and there would be a specific operation which would be performed at the level of a neuron. So let's take any neuron over here, right? So basically you have two inputs. One minute. Okay, so you have two inputs. You have input number one and you have input number two. And what you do is that you attach certain weights and biases to both of these inputs, W1 and W2. So what you basically do is that you let's say there are these inputs which are termed as x1 and x2. So we multiply the inputs by their weights, and then we add the biases as well. And this whole thing is later subjected to an activation function, and then the output is calculated. So at every node, we have weights which are associated with all the inputs which are coming in. So we have weights and biases, and we have an activation function, which can be either a tanh function, ReLU function, sigmoid function, etc. Now let's come to what's happening in cans. So in cans, let's say we stick around with the same structure. We have two neurons in the first layer. We have a set of five neurons in the second layer, and this is the final layer. So overall we have three layers. What happens here is that let's consider the first neuron, and will the connections remain the same, right? So let's say this is x 00, and this is x01, right? So the difference in cans is that instead of, you do not have individual weights which are associated with these connections, but instead you have uh, activation functions itself. So let's say now we consider this x00. What typically happens is that this x00 is passed through an activation function which just 1 minute. X00 is passed through an activation function which is, let's say, represented by phi 0 0, right? And then in the bracket we have x00 as the input, and then x01 is also associated with an activation function which is named as 501. So these are two activation functions, and what you do at the output is you simply do a summation of these both. So basically at the output you will have x00 of sorry 500 of x00 plus 501 of x01. That's it. So this will be the output which is coming from this network, this node, and it's connected over here. What are the differences you see? You do not see any weight parameters over here. You do not see any bias parameters over here. Now, the learnable parameters in CANs, therefore, are these activation functions which are named as 500 and 501 over here. And so, what are these activation functions, and how do we get to know about them? So, the basis of these activation functions are given by this thing called B-spline functions. So, what is a B-spline function? Um, okay, so B-spline function are basically, let's say if you have worked with CAD models before, if you recall, you would have, let's say you're trying to draw a curve, and then let's say there are these control points which you have at your disposal, and you are trying to control a curve using these control points. So let's say the curve has to pass through the first point and the last point, and let's say the curves goes something like this. Now what typically happens in these CAD applications is that using these control points you can change the shape of the curve completely. So you can have the one as the dotted a curve, or we can have a curve like these. And using only the five control points which I have described here, the entire curve can be controlled. Uh, so typically, when you have a B-spline function, you need to mention the number of control points, first thing. Second thing you have to mention is the order, which is represented by the symbol k. For example, if you want a cubic function, you would describe the order as 3. If you want a quadratic function, you would describe the order as 2. Now, using these two values n and k, we calculate the number of segments, which is n plus k minus 2. So let's say you have n equal to 5. So these number of control points are actually n plus 1. So here you would have 5 plus 3 minus 2, which is 6 segments, if you assume k equal to 3. What do I mean by 6 segments? By 6 segments, you mean what I mean is 1, 2, sorry, 1 minute. So I have 6 points over here because n equal to 5. 1, 2, 3, 4, 5, 6. And you have 6 segments which you can control, which means that, let's say, 1, 2, 3, 4, 5, and 6. These are the 6 segments. Right now I have drawn it as a rough approximator, but these 6 segments can be individually controlled by the control points in their vicinity. For example, the first segment over here is controlled by these control points 1, 2, 3. The second segment is controlled by the next 3. The third segment is controlled by next 3. The fourth segment is controlled by next 3, etc. Similarly, every individual segment in this B-spline function can be controlled by the number of control points. Now, okay, you might be asking the question, I have the number of control points, it is fine. How does the function typically look like? How do I make sense of the function? So, what typically happens is that, let's say, you have some functions. So there are basis functions, and any B-spline function is a linear combination of these basis functions. And these basis functions are, let's say, every control point is associated with one basis function. So let's say I have drawn here, and there is a mirror symmetry. So the second control basis function starts like this. Then you have the third one, which is, let's say, like this. Then I have to make a mirror image fourth one like this. And then typically you would have one basis function which is in the center. So what I have done here is that I have drawn 5 basis functions. And why do I have 5? Because every control point, 1, 2, 3, 4, 5, I have 5 control points. Every control point would be assigned with a basis function. So let's say the basis functions I denote as b1, b2, b3, b4, b5. And these points are p1, p2, p3, p4, p5. So the overall function would be p1 b1x plus p2 b2x plus dot 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 up till p5 b5x. So this would be the overall function, which is, let's say, 500 or 51501, which is represented over here. So every single function which we have to learn in the Kolmogorov Arnold networks can be represented as a B-spline function. Now, what makes this approach so interesting is that the theorem which came out almost 50-60 years ago, Kolmogorov Arnold representation theorem, it states that any smooth function can be represented as a three-layer network. Right, where, let's say, you have the first layer over here, the second layer over here, and the third layer over here. Now, they say that the second layer can be represented by 2n plus 1 neurons. So in our case, n was 2. So first layer had 2, second layer had 5, and then finally you do a summation of it all. So the theorem states that Any function, any smooth function can be represented as a three-layer network where these functions phi of q comma p, which are all these activation functions which we have to learn, are represented as b spline functions. Now what happened is that these 1D functions, if they were not smooth, people thought that we are not we will not be able to learn them in practice. Because of this theorem was basically sentenced to death in machine learning, and people thought this was absolutely useless because there is no way of using this theorem to represent unsmooth functions. What they have done here is that they have brought this theorem back from the dead, and then they have generalized this to a network with arbitrary width and depths. So what these people say is that, okay, it's fine. If you have an unsmooth function, what we'll do is that we will increase the number of layers in the network, and we will still use the same b-spline functions, and we claim that a CAN network with arbitrary width and depths can learn even unsmooth functions, which is basically the main contribution of this paper. Now we will come to the mathematical terminologies in one of the latter lectures, but today I also want to give you a visual representation of how cans work, and for that we'll be actually diving into a piece of code. So I will be sharing this particular notebook with you in the description section below. What we are going to do in this notebook is that we are going to have a two-layer can or a three-layer can, and we are going to represent a function using that. So the function that we have taken in this particular example, f of x is equal to, this is the function e raised to sine of x1 square plus x2 square plus sine of x3 square plus x4 square. So this particular example has been given in the GitHub repo itself, which is quite a nicely written repo. So sine of x1 square plus x2 square plus sine of x3 square plus x4 square. My task is that I have to build a can which is able to approximate this particular function. If the theorem what I just described is true, I should be able to represent a can which can approximate this function properly. So before we start this notebook, what all of you can do is that just open Google Colab, download the notebook which I have mentioned in the description, upload it over there. There are some things that should happen. First thing that you have to do is that you have to go to runtime over here, and then click on change runtime, and select this T4 GPU over here. This example only runs on GPU, and all of you should be able to do that. This is, I have not paid for Google Colab, so just click on this hardware accelerator. After you have done that, start executing the commands. Now I have already executed the first command, where I say pip install pycan, pip install torch vision. The pycan library is the one which is provided for managing the CAN networks, and it is an excellent library as we'll demonstrate. Now, the next piece of code is where we'll actually be training the CAN. Now, what we have written over here is, let's say model equal to, let's actually copy this line over here, and try to understand what's happening. Okay, so what's happening over here is that we have built a CAN like this: 4 2 2 1 1, which means that there are four neurons first, then there are two, one, and one. And then along every node, as I have described, there will be an activation function which we are planning to learn. So I'm drawing connections, and then these are the connections, right? Now, what does this mean? Grid equal to 3 and k equal to 3. So k equal to 3 describes the order of the functions that we are going to have order of the basis functions. How does that matter? So the number of segments are decided by this formula n plus k minus 2. So depending on the value of n, the number of segments which the grid will be divided to will be decided. And what about the number of control points? They are mentioned over here by this grid parameter. The more the value that we have here, the more finer grid we'll be having. So these are the different parameters, and then this second line you have to add model equal to model dot to CPU. Without this, there is an error which I was receiving, so I had to add this. The next one is where we mention the function, uh, which I have mentioned before as well, exponential of sine of x1 square plus x2 square plus sine of x3 square plus x4 square. And then we create a data set, and then finally we train it. We train the data set using this model. So and then after we run this, you can see the iteration slowly proceeds. So this is a simple piece of code using which you can okay, firstly, what all we have done here, we have firstly defined a can of a given width, number of grid points, the order of the basis functions first. Second, we have created an artificial data set, and then we are going to train our model to learn the activation functions to approximate that data set. Okay, this is learned. Now, what about the model? So you can see the training loss has almost reduced, and if we plot model dot plot, we can get a representation of the can. So as you can see, we have 4211, and okay, so from this particular neuron, we can see there is a connection like this to this second neuron, but you can see that there is no connection to the first neuron. Similarly, from the second neuron, there is a connection to this here, but there is no connection to the first neuron. So what we are seeing is that out of all the possible connections, the network is basically learning that there are some connections which are useless, then there are some connections which are useful. Whatever connections are useless are left out from the model architecture completely. So we are going to look at this also in detail. It's called a model pruning, and we are going to understand that how that is used to basically uh, increase the effectiveness of the training and reduce the training time. Now, this model dot plot function is pretty unique because all the curves that you are seeing here are actual functions which are learned by the model. For example, you can see here this is a quadratic function being learned by the model. This is a sinusoidal function. This looks like an exponential function. So this brings about a lot of interpretability in the solution. This is not possible with a traditional multi-layer perceptron approach. You have no idea how to interpret the weights and biases. What cans bring in is that they bring in a lot of interpretability because we can assign a symbolic form to these functions which have been learned. I can see that, okay, this particular function looks like a combination of a sinusoid, a quadratic function, and an exponential function, which is a great insight for me. So this particular command model dot plot is pretty powerful. So I hope one of the main advantages of cans have been cleared, which is the interpretability. How they are different from traditional MLPs is that we are not learning weights or biases individually, but we are learning the activation functions. Um, so I encourage all of you to download this notebook and try out this code in detail. And then in the next lecture, we are going to look at the mathematical formulations of all the different terminologies. If you have any doubts, just feel free to post them in the comment section, and we'll be happy to answer. Thank you very much.